Okay, we are off to chapter 6. Again, we are skipping chapter 5. We're never going to come back to it. Pretend it doesn't, but I suppose. So we're going to go chapter 6 here, exam 2 material, sorry. So in this chapter, there's a lot going on in this chapter. We're going to talk about bonding, obviously. We're also going to talk about naming and how to name everything. So let's get into it, I suppose. Yeah. So we're going to first start with naming, which is nomenclature. And when we talk about naming, as we will talk about towards the end of the chapter as well, there's really two types of compounds that we're going to sort of talk about in terms of naming. One type is an ionic compound or an ionic sort of bond. And with an ionic compound, that is always between a metal and a non-metal. And what happens when we do get a metal and a non-metal together, as we talked about in the end of that last chapter, because of those sort of periodic trends that we talked about, things like ionization energy, electronegativity, and those type of values, what happens is, as we talked about, metals typically have all the properties that they pretty much want to get rid of their electrons, right? They don't really want to hang on to electrons. They're not looking to gain electrons. Non-metals, on the other hand, have the opposite sort of situation. They have all the properties of like they want to hang on to their electrons, and they would also like somebody else's electrons. So when we get these two guys kind of together, what ends up happening is we do get a transfer of electrons. And the result of that is the metal becomes a cation, which, as we've seen before, is a positively charged ion from losing electrons. The non-metal becomes an anion, which is a negatively charged ion because it has gained extra electrons. And one of the things that we'll talk about later on in the chapter when we talk about bonding, which is there is actually no sharing of electrons here. So what holds sort of that bond together is the attraction there, which is sometimes referred to as the electrostatic attraction. Opposites attract to each other and no sharing of electrons. Now, on the other hand, when we get kind of two nonmetals together, that typically makes a molecular compound that has covalent bonds. And sort of in a covalent or molecular sort of compound, that's always between two nonmetals. And there is a big difference of what happens when we get kind of two nonmetals together. If you remember on the periodic table, they're all pretty much up there in the upper right of the periodic table together. Which means they have very similar properties. They have similar ionization energy, electronegativity, and they both have properties of, as I just mentioned, neither one really wants to kind of give away its electrons. They both really are looking to sort of gain electrons. So what happens when we get these kind of two nonmetals together that share similar sort of properties like that, they actually end up agreeing to share electrons. And we'll talk about in this chapter that sharing of electrons may be equal sharing, may be unequal sharing, but there's some type of sharing of electrons that holds together a covalent compound or molecular compound, which is usually between two nonmetals, as opposed to, say, an ionic bond, which is kind of between a metal and a nonmetal always. So we're going to talk about how to name kind of both of these sort of types of compounds that have these type of bonds in it. And then later in the chapter, we'll talk about how to get those bonds and where they come from. Now, one of the things that's important is, which I think we talked about, but just in case we didn't, if you look on the periodic table, as we talked about, most things, again, do not really have charges if they are by themselves from the periodic table. It's really only in the ionic situation that things do develop positive charges and negative charges. But when they do develop charges, there are certain places on the periodic table where things have sort of a fixed charge. And everybody in group 1, which is really lithium over there, has a +1 charge. Everybody in group 2, which is a metal as well, will typically make a +2 charge. If you skip the transition metal region there in the middle and go to group 3, usually in group 3, we're really just kind of talking about aluminum right around there. That will make a kind of +3 charge. And then we have group 4 that we skip. We go to group 5, 6, 7, and 8. And we do skip group 4. There's no real good pattern because it's kind of right where that staircase kind of comes down through there. But when we get to group 5 and we're talking about the nonmetals, which again is above the staircase, So we're talking about guys kind of above the staircase here. Guys in group 5 will make a -3. In group 6 will make a -2, and in group 7 will make a -1 charge. So it's kind of like +1, +2, +3, skip, and then go backwards, -3, -2, -1 in terms of charges. So for example, sodium, which is group 1, no matter what the situation is, it will always basically just make a +1 charge. One of the reasons for that, some of those trends we talked about, it has only one valence electron, which is its highest energy level electron. So as soon as it loses that, as we talked about, it gets really hard to try to take out any of those lower energy electrons. So sodium will always kind of just give away one electron always. Same thing with magnesium. Magnesium also has 2 valence electrons because it's group number 2 on the periodic table. So once you get through those 2 valence electrons, you're into those core electrons, which is held a lot tighter and not going to be lost. So something like magnesium kind of has a fixed positive charge. Transition metals, as we'll talk about, has a variable charge. And even these guys down here, places like lead, tin, antimony, bismuth, these guys, which are technically not transition metals, they are below the staircase, which means they are actually metals. And they do also have a variable positive charge. So in some situations, something like copper could be +1. In other situations, it could be +2. So it does have a variable charge. There is 3 exceptions, though, in the transition metal region that even though they are transition metals, they have fixed charges. And the 3 exceptions are right around here. I shouldn't have wrote too high there, but I'll just kind of come up here. There's zinc and cadmium, which is around there in the periodic table. Those guys, when they do make a charge, will always be +2. If you hang a left over there by cadmium, you'll get to silver, which is a +1 charge always. So those are kind of 3 exceptions. Thank you very much. Those are 3 exceptions in the transition metal region that, although they are transition metals, they also have fixed charges. And knowing whether or not, for example, a metal has a fixed charge or a sort of variable charge is really important in terms of the rules that you follow when you go to kind of name something that involves a metal. So as we will see, when the metals are involved, they are actually the most important thing in a sense. They kind of tell you how to name something based on what type of metal you have, one that has a fixed positive charge or one that has kind of a variable positive charge. Any questions on that so far? Okay. So in addition to specific names of how to name different compounds, there are certain things that do just go by common names. And H2O is water all day, every day. Yes. It's not a trick question on the exam. Just put water and take the point. Yes. Don't make me not give you the point by not putting water. Yes. I do enjoy all the funny names that people write for water, but it is water if you do see it. NH3 is ammonia. That's also a very common name. And CH4 is methane. That is the simplest organic molecule, which we will later see when we get into organic chemistry. The simplest one that you could have. I'll be honest with you, most people call NaCl sodium chloride, not really table salt, and sucrose here as well. But these 3 for sure, you should go by the common name, water, ammonia, and methane when you see them. So let's talk about naming compounds. And as I mentioned before, there's 2 types. We have our ionic sort of guys, which is a metal and non-metal. And by the way, as soon as you see that combination of metal and non-metal, you should know it's ionic. And it's pretty much the only thing that will have that sort of combination together. And when you see 2 non-metals, you should know you have some type of sharing of electron and a covalent bonding sort of happening. Again, some people will call those guys more molecular compounds, because they do share electrons. So let's talk a little bit about type 1 and type 2 compounds. And type 1 and type 2 compounds, they are ionic compounds. And they will always have a metal and a non-metal. And as we will talk about, there are kind of type 1 and type 2, and it's really the metal that determines what happens. And when we write a compound or a formula for an ionic compound, it is always the positive guy first and then the negative guy. So basically cation, then anion. That goes both for naming and also formula. So when you write the formulas, it should always be positive and negative. Also, when you put together a formula for an ionic compound, it should always equal 0 in terms of the charge, because it is made up of a positive thing, which is a cation, is made up of a negative thing, which is the anion. When you put them together to sort of write the formula, it should always be the simplest way to get to 0, basically, is it. So, for example, if I had calcium, which has a +2 charge because it's group number 2, and I want to put it together with chlorine or chloride there that has a -1 from group 7. Again, if I were to write the proper sort of formula for this, I want to put it together that it equals no charge. What that means is if I just stuck it together, one of each of them, I would end up with a charge because calcium is +2 and Cl is -1. That would leave me a +1 left over, right? 2 minus 1, basically. And that's no good. So you should never have a charge when you put a nonmetal, a cation basically, and an anion together. It should equal 0. So it's just a basic idea, just looking at the numbers. So 2 times 1 is 2. So I'm already at 2 for the calcium. To get this guy to 2, I need not 1, but I need 2 of those. And I basically have 1 calcium and 1 and 2 chlorines. The number goes to the guy to the left, so nothing written there means I have 1 calcium, and the 2 there goes to the chlorine, which means I have 2 chloride ions that each are -1. So it's really important to remember that when you do put a formula together for an ionic compound, the overall charge should equal 0. There is a reason for that, and we'll talk about when we get the bonding, but you never want to have a charge when you put them together. It's also really important, as we'll talk about as we go through this chapter, to remember that although when we put them together, it does not have a charge, it is actually made up of things that do have charges. So when we say we have calcium chloride, it's actually made up of things that have actual charges. Just when we put them together in our formula, it needs to equal 0, again, in the simplest way possible. Now, we have cations, which are positively charged. And typically speaking, we just simply use the whole name of the element for those guys. So if you had an Na+, that is what is known as the sodium ion. Right? We just use the whole name for the element. If you had K+, that is the potassium ion. If you had H+, that is actually the hydrogen ion. Now, a couple of things. If you are asked to write the formula for a cation, these are the formulas for these cations. And because they are cations, you do need to make sure that if you are asked to write the formula for an ion, it actually has the charge associated with it. Otherwise, it's not an ion. So you do have to write the charge. And typically, you do throw the word ion at the end of it if we're just naming the ion by itself. By the way, it doesn't matter if it's what the charge is. If we have Ca2+, that is the calcium ion. Yeah? So it works the same. It doesn't matter if it's +1, +2, +3 as well. Now, when we get to our negative ions, which are anions, we actually do a little bit something different in terms of the name. If we are just going to name the ion, we do take kind of the first part of the element name, but we do drop the last part. And sometimes we drop a little bit more than the last part, depending on the element. But we do kind of drop the last part of the name, and we replace it with IDE at the end. So for example, Cl-, Cl is chlorine. So instead of the chlorine, we drop the last part. This would be known as the chloride, IDE ion. Oxygen, which is group 6 there on the periodic table, has a -2 charge. Here we drop a little bit more than just the last part. This is known as the oxide, IDE ion. By the way, hydrogen, as we talked about, has some special properties. And one of the special properties of hydrogen is it's the only element that could kind of go both ways. It could be positive in certain situations. It could also be negative in certain situations. And that would be the hydride, IDE at the end of it, ion. So hydrogen is the only one that could kind of go both ways. Could be positive, could be negative. Hydrogen in most cases will be positive. It will typically only be negative if it comes after a metal. So typically if it comes after a metal, it'll be negative. It'll be the hydride ion. But in most cases, it usually is going to be the positive one. So once again here, if you're asked to write the formula for the anion, you do need to make sure, again, you include the charge. And if you had to just name an anion by itself, not with anything else, again, you basically use the kind of front part of the element name, drop the last part, put IDE on there. For anybody on the periodic table there, that is a nonmetal. Any questions on that there? Now, let's talk about type 1 and type 2 compounds and sort of what is the difference. And as I mentioned before, once again, these are ionic compounds, which means it is a metal and a nonmetal coming together. And once again, as I mentioned right there, if a metal is involved anywhere in naming, that's really what's going to kind of determine how you're going to name this compound. And the decision you have to sort of make is that metal a type 1 metal or a type 2 metal? And let's talk about what makes something a type 1 metal versus a type 2 metal. A type 1 compound has a metal that has a fixed positive charge. So if you remember, we just talked about it. That is any metal that comes from group 1, 2, 3 are zinc, cadmium, or silver. Any metal that comes from any of those locations on the periodic table will tell you that that is a type 1 compound. And then you could kind of proceed actually to naming the compound right at that point. And we'll talk about how to do that in just a second. But what those all have in common, once again, is they have a fixed positive charge. Now, a type 2 compound, you're still looking at the metal, but the metal will come from the transition metal region or just to the right under the staircase. You know, where, like I said, lead, tin, etc. is located. And what these guys have in common is also what we talked about, which is they can have a variable positive charge. So these guys will have a variable positive charge on the metal. And because of that, you have to do one additional thing when you name a compound that has a type 2 metal that you actually don't need to do when you name a type 1. So that's the major difference, is the other thing that you have to do if it's type 2 versus type 1. As I mentioned before, something like chromium could be +2 or +3 depending on the situation. Copper +1, +2. Iron, for example, could be +2 or +3. It sort of depends on the situation. Again, because they could have a variable charge. So that's always kind of when you go to name things or you're thinking about naming something, these are the things you should sort of think about in this order is, what am I dealing with? Am I dealing with like a metal and a nonmetal, or am I dealing with two nonmetals? And if the answer is a metal and nonmetal, then you should always turn your attention to the metal and decide, is it a type 1 metal or a type 2 metal? We're going to talk about again in a second here the difference of what you need to do depending on which one is. So you just kind of want to go through that checklist as you are trying to name something. And again, it should hopefully point you in the right direction. Here is a table for your book. I'll spit that out maybe. And again, we have our positive ions on the left there. And again, you can see we basically just use the name of the element with it. And we have our negative ions on the right, and they all have, again, the IDE treatment at the end. Again, some take a little bit more than the back part of the element name off, and some a little less. And you'll kind of get the hang of it as you kind of go through it. So let's talk a little about type 1 ionic compounds and how we go about naming them. So as I mentioned before, type 1 is our metal and nonmetal. And again, always looking at our metal here. And once again, that's going to be a fixed positive charge. That's going to be group 1, 2, or 3, zinc, cadmium, or silver. So for example, one that we had earlier there, we did our CaCl2. Again, the thought process as you go through this is, what am I dealing with? All right, so I see this guy is a metal, that is a non-metal. That automatically should scream to you ionic. Now, once you do that, I know I have a metal involved. That is where you should just turn all your attention to. And you basically want to find where it is located on the periodic table. And calcium's in group number 2. And because it's in group number 2, it has a fixed positive 2 charge, which tells you this is a type 1 metal. At that point, there's really nothing else you need to do to name this thing. You just roll with the rules. And the rules to name a type 1 compound is pretty straightforward. For our metal, we just roll with the whole name. Yeah. Does not matter how many you have of it. You just roll with the whole name. Yeah. The non-metal gets the IDE treatment at the end. So we're just going to drop the last part of the non-metal name and put the IDE. So as soon as I see this is a type 1, I'm going to go with the whole name there, calcium. And the non-metal gets the IDE here, yeah? And that is calcium chloride. By the way, the 2 here does not affect the name. You should never, ever, ever, I'll do it 2 more times for good measure there, ever use a prefix in this situation. People always want to go dichloride because it sounds more chemistry-like. It sounds like you're going to get a big X, yes, and then you get it wrong. So don't do that. There is a place for prefixes, and I'll just give you the hint here. If there's a metal involved, that is not the place, yeah? So if you have a metal and you start laying up some prefixes, you should also probably lay up some X's on the paper because you're going to get some X's over those things, so do not do it. So the good way to remember it is, if you got a metal, you should not be prefixing anything, yeah? The 2 is there for obviously what we talked about earlier. The 2 is there because we need to get our charge to 0. And it's there basically to tell us that this thing is made up of basically ions. And we have 1 calcium ion, that's group 2, is +2. And we have 2 of these Cl minuses, which if we add them together is -2 and +2. Everybody's balanced out to 0. And that is what the 2 represents there. By the way, if you were asked to write the formula for the anion here, this would be the formula for the anion. This is not the formula for the anion. Yes, the 2 does not go there. Yeah, so the 2 is just simply telling you you have 2 of those Cl minuses. And if you're asked again to write the formula for the anion or the cation, you need to just write the proper formula for each of those. And again, no prefixes in this case. Just like we saw earlier, right? NaCl. Na is a metal. Cl is a non-metal. So once again, this tells me ionic. Check. I look at my metal. I find it on the periodic table in group number 1, which means it has a fixed positive charge. It's always going to be +1. So that tells me this is a type 1. Check. That means that's all I need to think about at this point. I can good to name it. Whole name of the metal, sodium. IDE there on our non-metal and sodium chloride. Questions on that there? So in general, as we talked about, when we do put the formulas together, we always want to get them together, as we talked about, in the simplest way to get to 0. There are many ways to balance out the charge, but you always want to make sure that kind of the subscripts on the bottom are the simplest kind of ratio that gets you to 0. If not, you should reduce it down to the simplest number. If you have to write, like we talked about, the individual ions, you do need to show the charge to indicate that they do have charges. Obviously, when we put them together, no charge for either thing. So again, if we look at this guy, which is Ki, that is a metal. That is a non-metal. So once again, that tells me ionic. Looking at my metal, that is group 1, which tells me this is a type 1, and that is all I need. I could just roll right into the whole name of the K, which is potassium, and iodide, IDE for our iodine, and that would be potassium iodine in this case. It is made up of 2 ions. It is a group 1 ion, which has a +1 charge. That's the potassium ion. And it is a group 7 ion that has a -1 charge, which is the iodide ion. +1 and -1, when we put that together, equals 0, which is why we just need one of each of them. That's why the formula, again, is Ki in this case. Any questions on that there? All right, so why don't you try some, and why don't you also try doing the formula as well? Let's do magnesium. Do magnesium nitride. Let's do lithium oxide. Let's do sodium. Let's not do sodium. Let's do aluminum oxide. No, let's do aluminum sulfide. That's even better. All right, on the left there, we want the proper name. On the right, we want the proper formula. So see what you come up with. I got potassium, which is a metal, Cl, which is a non-metal. So again, that should check the ionic box. Once again, there's a metal involved, so that is really where I should turn all my attention to. And that is potassium, which is group 1 on the periodic table, and it has a +1 charge, a fixed charge. That tells me it is a type 1, and that's all I need to name this, right? So again, just going to go with the whole name of the first element there, the metal, which is potassium. And once again, here our second guy gets the IDE treatment at the end, which is potassium chloride. This again has no charge to the overall formula, but is made up of a cation that has a +1 charge and an anion that has a -1 charge. And again, that's why the formula is basically KCl. One of each is all is needed to get to 0. Any questions on that one there? Looking at the next one, again, metal, calcium, non-metal, bromine, checks the ionic box. Metal involved, I look at it, that's calcium. Again, group number 2 on the periodic table, which means it's a type 1 metal, has a fixed positive charge. So we'll check that box off. Once again, that is all I need to name this. I could care less about anything else at this point. That is calcium bromide. Once again, no prefix on that. Once again, this is a guy that is basically calcium with a +2 charge. Bromide is group 7, which means, again, it is Br minus. The 2 here means I have not one of those, but I have 2 of them floating around in the solution, most likely. And again, both of those together gives us a -2 that balances out the +2 charge that comes from the calcium. Any questions on that there? Coming to our last one here, that is barium, which is a metal. And that is hydrogen, which remember is a non-metal, even though it's kind of hanging out over there in group 1. So it's ionic. And in this case, barium is group number 2, which means it will have a fixed positive charge. And that is all I need here. That's going to be barium. And this is actually hydrogen coming second after a metal. So what we actually have here is barium that has a +2 charge. And because hydrogen, when it comes after a metal in an ionic compound, is the negative version of it, which is H-. And once again, the 2 is here to tell us we have not one of those, but we have 2 of them. That gives us a -2 that balances out the +2 from the 1 barium. And again, this also gets the IDE treatment at the end of it, and it is barium hydride. Any questions on any of those there? Now, when we want to write the actual formula for a name, we kind of work backwards. What you want to always kind of start with is just the basic units that make it up, in this case, ions probably. And when we see magnesium and nitride, magnesium, I know hopefully is group 2 on the periodic table, which means because it's group 2, it has a +2 charge. And by the way, magnesium is a metal and nitride is nitrogen on the periodic table, which is a non-metal. And that also tells me it's ionic here. And nitride is nitrogen, and nitrogen is group 5, which means it actually has a -3 charge. So once again, this is an ionic compound because we have a metal and a non-metal together. We want to put it together to get to 0 in the simplest way possible. If you're not sure how to do that, just multiply the two numbers together and you get a 6. Yeah, so that's probably the simplest way to get there. So to get my magnesium to a 6, I don't need 1, I don't need 2, but I actually need 3 of them to get me to 6. To get my nitrogen there to 6, I don't need 1, but I need 2. So if it helps you to draw it out like that, do it. Because at this point, all you have to do is just count. I have 1, 2, 3 magnesiums. So you go Mg3 on the bottom, right? Because it goes to the guy to the left. And I have 1 and 2 nitrogens. And there you go, right? So again, -6, balancing out the +6 in this case. Any questions on that? Now, sometimes people are taught to like bring the charges down and then also bring the subscripts up to figure out the charges. And if you want to do that, you can. It'll just be right about 93% of the time. So if you're good with that, it will not work 100% of the time. But maybe it's better just to kind of figure it out like we're doing here. But again, sometimes people are very commonly taught just kind of move those things up and down. But just a cautionary note on that, it will not work 100% of the time. Yeah. So let's take a look at the next one. Lithium, which is a metal. Oxide is oxygen, which is a non-metal. So again, that checks the ionic box for us. Lithium is group 1, so that's going to have a +1 charge as it has a fixed positive charge. Oxide, which is oxygen, which is group 6 on the periodic table, should have a -2 charge. And once again here, we need to put this together to equal 0. So you could even do 2 times 1 is 2. So we need to get them both to 2 here. So hopefully you can see that you actually need not 1, but you need 2 lithiums to do that. And once again, you can count. I got 2 lithiums, so that's Li2 and 1 oxygen. And there you go. Yeah, so you'll have the right one. Again, number goes to the 1 to the left. If there's nothing written, it's assumed to be 1. So we typically don't put the 1, on the oxygen. Lastly, here we have aluminum, which is a metal. We have sulfur, which is a non-metal. And aluminum is group 3, which is a +3. Sulfur, which is where sulfide comes from, is group 6, which is a -2. So once again, if we multiply those two numbers together, that's a 6. So we need to get everybody to 6 basically. So aluminum, we're already at 3. So we need 1 more there to get to +6. And here we need not 1, not 2, but we would need 3 of those -2s to get to -6. And that means I have 2 aluminums and 1, 2, 3 sulfurs. Yeah. There you go. Yeah. Any questions on that there? All right, so the goal there, like I said, is to make sure you kind of get no charge on the overall thing. But once again, it is made up of things that do have charges, and you got to get it to 0 in the simplest way possible. Any questions on type 1 here? Yeah. Then let's talk about type 2. Type 2 is also an ionic compound. So once again, we're going to have our combination of metal and non-metal together. And just like the last one there, the metal, once again, is going to be the most important thing here. So the difference between type 1 and type 2 is actually the metal and where the metal is located on the periodic table. The metals for type 2 are going to be in the transition metal region, or just to the right. And what those have is a variable positive charge. So we actually do name it the same way as we name type 1, except that we do need to put one additional thing in. And we still do the whole name of the metal. We still go with the non-metal that drops the last part and puts IDE. The additional thing that we add for a type 2 is in the middle, we use a Roman numeral. So we do use a Roman numeral in the middle. And what the Roman numeral indicates is the positive charge on the metal. So if you took one of those metal ions out by itself, what the positive charge is. Very often confused by people is when they start doing this, they think the Roman numeral means how many of the metals you have. And that is not what it means. It means if you took one of those guys out, what the actual positive charge is. So that's a really important thing to keep in mind. Now, for example here, iron FeCl2. So if we were to work through this, we would still go through our same sort of process here. That is iron, which is a metal. That is Cl, which is a non-metal. So once again, that will check off the ionic box. We look at our metal, always the most important thing there. And we find our metal dead center there on the periodic table. Dare I say 26, maybe, hopefully. And that is in the transition metal region. So when you see that, it should indicate to you that this is a type 2. This has a variable charge. So we do have to kind of figure out what is the charge on the metal if you're not sure. So the way you could go through that is very simply, we do know that we just have one of those metals there, right, based on the formula. The good news is you will always know the charge of whatever it's hooked up with. So in this case, it is hooked up with Cl, right? And Cl is group number 7 on the periodic table, which means Cl has what type of charge in group 7? Group 7 is -1, yeah? So it does go +1, +2, +3, skip, and then starting at group 5, -3, -2, -1 backwards. So kind of up to 3 and then down to 3 on the other side. But we don't just have one of those Cls, we have 2 of them, right? Which is really important. That means overall here we have a -2 sort of charge from the 2 Cls. Remember, it has to equal 0, so that would tell us that the iron in this case has what type of charge to balance it? It has to have a +2 charge to balance it, right? And that is the one thing that we have to kind of figure out here when we're naming these. We proceed the same way. We go iron, Roman numeral 2 in this case for the charge, not how many metals you have, but the actual positive charge on that metal. And once again, it does not matter how many of you have here. Once again, no prefixes. And I know that because I still have a metal involved, right? So that's a good way to remember it. I'm not going to prefix with any type of metal. And this is just going to be chloride. Yeah. So this would be iron 2 chloride. The 2 again is telling people in this particular case, the iron is carrying a +2 charge. Now, why do you need to tell people that? Well, that's really what naming is about, is telling people what things are. And let's just say, for example, I had FeCl3. Once again, metal, non-metal, it's ionic. Looking at our metal, which is still iron, which tells us it's a transition metal and a type 2 metal. Once again, I may not know the charge, but we do know Cl is still group number 7, which has a -1 charge. But in this case, we don't have 2 of those. We have 3 of them, which gives us a -3 overall charge. In this case, the iron is actually going with what type of positive charge? +3 to balance it out. So not the +2 in this case. And that is why when we name this guy, this would be iron Roman numeral 1, 2, and 3 for the charge, and this would still be chloride. So when we have a type 2 metal involved, we actually have to use a Roman numeral to tell people, hey, in this case, this is the iron with the +2, or in this case, this is the iron with the +3. We do not need the Roman numeral on a type 1 because it is fixed. So when you have sodium, it could only be +1. You don't need to tell people that because it can never, ever be anything other than +1. So we don't use Roman numerals on type 1 compounds because that metal is always fixed charge. It'll never be anything other than what it should be. But we use a Roman numeral to indicate the charge on a type 2 metal because it could vary depending on, who it's hooked up with, what the situation is in that time. But you will always sort of know the charge on what it's hooked up to, so you can just kind of work backwards to figure out the charge if you're not sure. Any questions on those there? All right, that's pretty much what's underneath the scribble there. All right. Okay, so let's take a look. PB, by the way, is lead, yeah, and that is a metal. Oxygen there is obviously a non-metal, so this definitely is ionic. We're going to look at the metal. The metal there is not really a transition metal, but it is one of those ones just to the right and underneath the staircase. So remember, just to the right and underneath the staircase are metals, and they have positive charges, and they also have variable positive charges. So it is a type 2 in that region. So once again, here we have 1 PB. We have oxygen, which is group number 6 on the periodic table, which means it is a -2. We don't have just one of them, but we have 2 of them. That gives you a -4 charge. That means in this case, the lead is going to be +4 in this case to balance it out, not +2. And that would give us lead Roman numeral 4 for the charge. And once again, oxide in this case, no prefix. This is one of those ones I was talking about earlier that if you just kind of brought the charges up, you would get it wrong. Yeah, you would end up with 2 instead of 4, which it should be. So again, doesn't work 100% of the time. And that's an example of one where it would not work right. Question on that there. Now, there is an older sort of system of naming these guys with Roman numerals, and we're not going to use it, but uh, the older way is the one that has the higher charge will end up with ic. And they also use kind of the historical name for the elements. So instead of like iron, it'll be like ferric or ferrous, OUS for the smaller charge. Copper would be cupric or cuprous. We're not going to use any of those, but sometimes they still kind of pop up in some places, especially copper and iron, which are popular things. But we will strictly use Roman numerals here. We will not use like ferrous chloride. We would call that iron 2 chloride like we did on the previous slide. And there you go. Now, one kind of weird one that always confuses people maybe is mercury. And mercury, we have this. And we also have this. And oddly enough, the one that has all the 2s is actually mercury 1. So this is mercury 1. I'll just abbreviate there. And the one that has just 1 2 is actually mercury Roman numeral 2. And that's because mercury 1 comes as a dimer. It's basically 2 1s together. So that's why there's a 2 on the bottom to indicate there's 2 actually mercury atoms. And the 2 on top is because +1 and +1 gives you +2 when they come together. How do you know it is the first one versus the second one there? Usually that bottom 2 will hang out if it is that. So for example, if I had Hg2O versus HgO, yeah. This one has the 2 there. That's actually mercury 1. It has the 2 on the bottom. This one, no 2 there, is actually mercury 2. So usually that extra 2 on the bottom will hang out on the mercury 1 to kind of indicate that that's probably the mercury 1 that you're dealing with. So you'll kind of see that 2 like you see here, usually still in the formula when you kind of look at it. So that's a way you can remember it. All right. So as we talked about, we are going to use that Roman numeral in parentheses. And once again, it is the charge of the positive ion in that case. So let's try some here. I want you also do some formulas. So let's do iron Roman numeral 3 oxide. Let's do nickel 4 bromide. And let's do actually, let's do not that. Maybe let's do. Yeah, let's do it. Why not? Let's do gold to oxide. Gold is AU, by the way. Yes. All right, so names on the left there and formulas on the right. to try and identify what we're dealing with. Cobalt's a metal and Cl is a non-metal. So again, that should check off for you the ionic box. We then want to look at the metal because it's involved in cobalt, also in the transition metal region, which should again tell you type 2. That also should tell you that you need to take the additional step to figure out the charge on the metal so that you can use a Roman numeral. So that also tells us Roman numerals are involved as well, right? So we need some Roman numerals. All right, so we might not know the charge on the cobalt, but we do know chlorine is group 7, which means it has a -1. And there are 3 of them. So if it helps you, just draw out pictures sometimes. And that's a -3 overall. That means since there's only one cobalt to balance it out, we are looking at a +3 to do it. And again, that is all the information we need. We're just going to go with the whole name there of the metal, which is cobalt. Again, the Roman numeral is not how many we have, but the actual positive charge on it. And just like last time, we have a metal still involved, so no prefixes or anything crazy like that. We're just going to go chloride IDE at the end, yeah? Any questions on that one there? Taking a look at the next one, we have Cu, which is copper, which is a metal, I, which is iodine, which is a non-metal. So again, should check the ionic box. Looking at the metal, which we always want to look at if it's involved. Copper also towards the center-ish or to the right-ish of there, the transition metal, number 29 up on the periodic table. That tells us it's a type 2 and we need a Roman numeral. So once again, I have 1 copper. I do have 1 I, and I is from group number 7 on the periodic table that has a fixed -1 positive, -1 charge. That means to balance us out to 0 here, our copper actually would be carrying just a plus charge in this case, or a +1 charge. Again, that is all we need to figure out. So that's going to go copper whole name, Roman numeral 1 for the charge, and iodide here for our non-metal. Any questions on that one there? Coming to our next one, we have SN, which is tin, and that is a metal. Br is a non-metal, checks the ionic box. Looking at our tin, it is not in the transition metal region, but once again is one of those guys to the right there by lead and stuff underneath the staircase, which is treated in terms of naming the same way as if it was a transition metal. So we do need to figure out our charge here and our Roman numeral. So we have one of the SN. In this case, we have Br, which is group 7, which means it definitely has a -1 charge. There are 4 of them. So if you want, you could draw out 4 of them if it helps. That is a grand total. If we add up all of that negative charge of -4, once again, we need to equal 0. So that will then make my 10 a +4 in this case, giving me 10 Roman numeral 4 for the charge. And a bromide here, yeah. Any questions on any of those names? Yeah. Doing good, yes? Okay. All right, going to the right here, we're going to put it together. So this one is not too bad. There's not much to figure out. The reason for that is when I see iron Roman numeral 3 oxide, I definitely know it's a type 2 because that's the only guy that has a Roman numeral. I also know it's ionic because it's the only thing with a Roman numeral. And I also know that the iron here has what type of charge? +3, because that's what the Roman numeral means, right? So I don't even have to figure that out. It basically just tells me. Oxide is oxygen on the periodic table, which means it's group number 6, right? And that should have a fixed -2 charge. So once again, we just want to put this together to equal 0. So again, if you want to multiply them together, you can. 3 times 2 is 6. So to get my iron to 6, I need not 1, but 2 of them. Get my oxide to 6, I need not 1, not 2, but 3 of them. And that means I have 1, 2 irons. Let me write the E first. And I have 1, 2, 3 oxygens. There it is, yeah, in terms of that. Any questions on that one there? Once again, here I see a Roman numeral, which tells me it definitely is type 2. That means it's ionic. And that also tells me here my nickel is rolling with a +4 charge, right? And bromide, which is group number 7, has a -1. So 4 times 1 is 4. So I'm already at 4 with my positive guy. So I need to get my negative guy to 4, which means I do need 4 of them. That gives me a -4 to balance out that +4. And now I'm just going to come down here, I think, to write it. I got 1 nickel and 1, 2, 3, 4 BRs. And there you go. Yeah. In terms of the formula. Any questions on that one there? Lastly, here we got gold, Roman numeral 2. So gold is AU up there on the periodic table. Transition metal will have a +2 charge because of that Roman numeral. Oxide, which is group 6, will have a -2 charge in this case. I'm just going to need one of each, right? Then that's going to get me to 0. +2 minus 2 equals 0. Any questions on any of those type 1, type 2s? Yeah. Our naming now. Doing good? All right. Yeah. The spelling count, yeah, I'm gonna say yes. How's that? Try to spell it as close to right as you can, as possible. Yeah. All right. All right. The next thing we're gonna talk about is again some other ways to name things, but first, just a reminder of what we just talked about, which is again really type 1 and type 2 compounds, and the only difference between type 1 and type 2. Again, does rely upon the metal. And if your type 1 metal has a fixed positive charge, which means it goes from group 1, group 2, group 3. Remember as well, though, also those 3 transition metals, zinc, cadmium, and silver, they also have a fixed positive charge. So you do not need to use a Roman numeral with those 3 because, again, it's +2 for zinc, +2 for cadmium, and +1 for silver. Again, outside of that, pretty much the rest of the transition metal region, and just to the right, as we saw in some of those examples, they will need a Roman numeral. And like we did in those examples there, what you want to do is just sort of figure out the charge of whatever it's attached to. And remember, it has to equal 0, so that will help you figure out the charge on the metal. So the next one that we're going to talk about is our type 3 binary compounds. And type 3 is different. Type 3 is actually 2 nonmetals together. So the difference here is we have no metals. We have 2 nonmetals, and we're going to have sharing of electrons that's going to kind of hold that together. That's different than our ionic guys, which again do not share electrons. They're held together by opposite attraction, positive and negative attraction of each other. This is actually the place where we do use prefixes. So as earlier said, there's a time and place for prefixes, and this would be the time and the place for prefixes here. So we do use prefixes, as we will see: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, maybe a nona, could be making it up, I don't know, deca maybe, sounds like a good 10 there. So this is the place where we do use these prefixes. They are actually, to be honest with you, I think probably the easiest ones to name and write formulas for, but they are unfortunately the ones that most people kind of screw up on a lot because they think it's got to be like harder than that or what to do. So they try to do all kind of funny things with it. But it is a pretty straightforward one here. So let's talk a little bit and we'll see that chart, I think, in just a second here again. Plus you. Type 3, again, only contains 2 nonmetals together, much like how we could recognize kind of type 1 or type 2 because it's a metal and nonmetal. Here we see 2 nonmetals we know as type 3. That, again, what that should signal to you is prefixes, yeah? So just like type 2 should signal Roman numerals, and just like type 1 should signal nothing. You don't need anything there, right? So those are the things you kind of want to think about as you're going through it. So the rules for naming our type 3 compounds are pretty straightforward. That's not the right table in your book. We do go with the first element that's written in the formula, and we use the whole name of the first element. And we do use a prefix if necessary. So prefix in the first element name, and that's just the whole name. Then we use a prefix on the second element. And the second element gets named with the IDE at the end, just like a normal non-metal name. So kind of the second one here comes with normal IDE at the end. You do put a prefix in there. Now, there are a few rules, and one of the rules is we do not use mono on the first name, but it is okay to use it on the second name. So no mono on the first name. Okay on second. The other thing that occurs a lot of times when we name these type 3 compounds and we use these prefixes are the ending of the prefix and the beginning of the element name. We'll put two vowels like back to back. So sometimes you may get like an O and an O that sort of backs up to each other, one from the prefix ending, one from the element starting. Or you may get like an A and an O that sort of backs up to each other. Same deal, one from the prefix, one from the actual element name. Now, typically when you have this situation, what we do is we get rid of the prefixes vowel, and we keep the elements vowel. So those are kind of the two main rules. No mono on the first, mono's good, all good on the second. And once again, if you got kind of two vowels, an OO or an A and O, you get rid of the prefix vowel. Two I's are okay, but the double O's and the A and the O is not. So let's just take a look at an example of this, which will, I think, pretty much hit all three of those rules. We'll go with C and O, right? So that's capital C, capital O. So the first thing we want to do is just like we did before, C, which is carbon, and that is a nonmetal. O is oxygen, which is a nonmetal. So that tells you it is going to be covalent. They're going to share electrons. It also tells you it is a type 3, which tells you I do need prefix. So the nice thing about this is there is no ions involved in these guys because there are sharing of electrons. There's no transfer of electrons, which means you don't have to figure out charges. You don't have to figure out anything. All you simply have to do is figure out how many of each one you have and pick the right prefix. So I have here one carbon, right? And the prefix here is mono for one. I have one oxygen. Prefix for one is mono. And that's pretty much it. You're ready to basically name it at this point. Just want to follow the rules. Will I use mono on the first name? No, that's one of the rules. So we don't use mono on the first name. So in this case, we would just use the whole name of the element, which would be carbon. We can use mono on the second name. That's all good. So we could go with mono. And then again, the second element gets the IDE, just like we did previously. So this would be oxide, right? What just came back to back there? So we do not call this carbon monoxide, right? We call it carbon monoxide, right? So here we would get rid of the O there, and this would be carbon monoxide, yeah? Any questions on that there? So they really are the simplest in the sense that you don't have to really figure out any type of charging or balancing anything. You literally just need to figure out how many you have, which you can find from the formula, and pick the right prefix and obviously avoid those three rules, basically. Yeah. Any questions on that there? So here again, whoops, here again are our prefixes. Our mono, not used on the first, di, tri, tetra, penta, hexa, hepta, octa. And once again, that OO or AO, we're going to drop the vowel off the prefix. Again, usually that's going to happen if you got kind of oxygen a lot of times coming out as the element on the second one. You'll run into a lot of those. Other things, again, as I mentioned, tetra is another example of that. Once again, we would not call it tetraoxide. Here we would drop the A off of there and just call it tetroxide here with no A. And then there's our mono there where we, again, will drop the O off of there. We still have some of our common names that we talked about at the very beginning. Water is basically non-metal sharing of electrons. So that is H2O. That is dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide, right? It doesn't sound very refreshing, right? Water has a much better ring to it than that, right? So don't come up with weird names. Same thing here, ammonia. This is not nitrogen trihydride. This is ammonia. And our methane, which is this guy here. Now, one thing I do want to talk about here before we continue on with this, which is hydrogen. So as we talked about, hydrogen obviously is a non-metal, and hydrogen can be hooked up with another non-metal like Cl. We actually do not name this like a type 3 compound. As we talked about maybe previously, hydrogen's hanging out over there in group 1. We actually will name this kind of like a type 1 compound, even though hydrogen is a non-metal. So we would just call this hydrogen fluoride, yeah? So no prefixes or anything like that, especially if that's a gas, it would be hydrogen chloride. By the way, if it's an acid, which looks the same, it would be hydrochloric acid in that case. So it does kind of depend. So hydrogen is basically, if you have hydrogen like that, just kind of name like a type 1 compound, even though really it is non-metal. Non-metal, really it is those guys sharing electrons in that situation. But in terms of naming, we kind of name it like that. Even if you have multiples like H2S, a little hydrogen sulfide. So just like before, no prefix, and that's hydrogen sulfide gas, toxic, smelly gas along the way. So hydrogen, again, is sort of an exception, even though it's a non-metal. And again, one of the reasons it does share a lot of similarities with a lot of things in group 1. So it's sort of named that way. Any questions on that there? All right. So why don't you give those a go, and we'll give me some names here. Let's do dinitrogen pentoxide. Let's do sulfur hexabromide. And let's do carbon tetrachloride. Let's do one that probably doesn't exist, but why not? Dioxygen try something. Let's try something here. Let's go. Let's try trifluoride. Okay, let's take a look. So once again, we'll go through our process here. I see I, which is iodine, which is a non-metal. I got O, which is oxygen, which is also a non-metal. So once again, that should check off that type 3 box, which should make you happy because, again, there's really nothing to figure out other than just kind of pick the right prefixes, right? So I got 2 here. So the prefix for 2 is di, right, for the 2. And remember the first element, we just use the whole name. So diiodine. And again, here the 2 I's are all good. The second one, we have 7 of them, which means the prefix for 7 is hepta. And the second element gets the IDE at the end of it. So here we will need to drop the A off of the prefix because that oxygen is going to put an O there, right? And we'll get heptoxide here. So diiodine heptoxide, again, really should be the fastest ones you do because there's really nothing to figure out in terms of balancing charges or anything like that. Yeah. Any questions about that? Coming here, once again, I see carbon, which is a non-metal. I see oxygen, which is a non-metal. Should tip off the type 3 sort of box there. Here, we're going to go 1 for our first one, which is mono, which we do not use. So we're just going to default to just the name, the whole name. Second one, we do have a 2, which means the prefix for 2 is di. And again, the second element gets the IDE. So this would be carbon dioxide in this case. Yeah. Any questions on that one there? Lastly, here we see phosphorus, which is a non-metal, chlorine, which is a non-metal. And once again, we have 1 phosphorus. We're not going to use mono on the first name, so that is phosphorus. We are going to use prefixes there for sure here on the second name. And that's 3 of them, and the prefix for 3 is tri. And it's going to be chloride in this case, yeah? Any questions on any of that? All right, then probably the quickest of them all is what we got going on the right-hand side. We basically just need to write what is there. The first thing I should look at here is I see what in the name. I see prefixes, right? So that tells me I don't have to worry about anything in terms of balancing. I'm just going to write what it says. So I know di means 2, right? And nitrogen is N, so I just go N and 2, and I'm done with that name. Penta is 5, oxygen is O, so O5, and there it is. Yeah, again, nothing to balance. Pretty much just need to write what is there. Next one, I see sulfur, although I do not see a prefix here. I definitely see a prefix here, and the only place prefixes can happen is in this situation with type 3. So when I do not see a prefix on the first one, I know how many do I have? 1, right? Because we don't use mono on the first name. So that's just going to be an S. And hexa is 6, and bromide is Br, and a 6. Yeah, so that would be right there. Same thing on the next one. I see no prefix, but I definitely see a prefix. So again, going to be type 3. No prefix on that first one tells me there's just one of them, so that's a C. Tetra is 4, and chloride is Cl, so that's a Cl4. And there we go. And lastly, double prefix action here. Definitely telling us it's type 3. Di is 2, oxygen is O, and tri is 3, and fluoride is F, and my made-up thing here of O2F3. There we go. Any questions on type 3? Again, they really are the easiest, but people do want to kind of mix and match things and kind of mess it up there. So don't do that. Hopefully you can see at this point, right, we have not mixed and matched anything. What I mean by that is I have not used a prefix and a Roman numeral together. That is also going to be probably wrong in most situations. There's only one specific place where that might ever happen, and we'll talk about it here in just a second, but pretty much they should never mix over. So again, prefixes for type 3, Roman numerals for type 2, and nothing for type 1. Yeah, any questions on that? All right, the last type of naming we're going to talk about, and here again are our rules as we go through it, is polyatomic ions. And polyatomic ions are groupings of nonmetals that are together, and they actually do have a charge. So they are ions. They are weird things in the sense that they actually are covalently bonded together. They're actually sharing electrons, but overall, the overall thing has an actual charge because of the way they are sharing electrons and what's involved in that. So polyatomic ions are groups of nonmetals together that have specific names and specific charges associated with it. For example, if we take this guy right here, NH4, NO3, and we put a line kind of badly between those two spots right there, we actually have 2 different polyatomic ions in this particular case. We can do a little better on this one. Let's try this again here. Maybe. Going this way, we have a nitrogen and 4 hydrogens, and that entire thing has a +1 charge. So that one nitrogen and those 4 hydrogens, they are bonded together through sharing of electrons, which means they will never, ever break apart into individual things. They will move around as a group. Wherever it goes, they will all go together. And it all together, all 5 of those things, the 1 nitrogen, 4 hydrogens, has a +1 charge overall. So it makes it an ion because overall it has a charge. And once again, we never break up the kind of nitrogen, hydrogens. They'll just kind of move around as one unit. This over here is 1 nitrogen and 3 oxygens. It actually has a -1 charge. So same idea here, that 1 nitrogen and those 3 oxygens are bonded together through sharing of electrons. They move around together. They never break apart. They all just kind of move as one unit. And the overall thing has a -1 charge. So ultimately, as you can see, this is an ionic compound because I got something with a positive charge, right? And I got something with a negative charge. And our rules when we put something positive and negative together is it needs to equal what type of charge overall? 0, right? So in this case, we have +1 essentially, even though there's a lot of stuff there. There's basically just a +1 on the left and a -1 on the right. So when we put these together, we just need one of each of them, which is why we get to that first formula that is there. And again, it's ultimately still just like we did with like type 1 and type 2, positive and negative things coming together equals to 0. Now, each of these polyatomic ions has a special name. This is what is known as the ammonium ion, not to be confused with something we saw earlier, which is NH3 with no charge and one less hydrogen. That is ammonia. Ammonia is not a polyatomic ion because it does not have a charge, but is oftentimes confused with NH4 plus because they look very similar to each other. They actually are related to each other, but the NH3 is not a polyatomic ion. So that is actually something different than a polyatomic ion than we have here. NO3 minus is the nitrate ion. Now, sort of the good news is that polyatomic ions, we simply just use the name of them. It doesn't matter how many you have of them. It doesn't matter if you have more than one. We just simply use whatever their name is. So in this case, we would use the name of this polyatomic ion, which is ammonium, and the name of this polyatomic ion, which is nitrate, and that thing there would be known as ammonium nitrate. Now, what is the deal with polyatomic ions? Well, the deal is this. There's very few positive polyatomic ions. That ammonium is one of the few positive polyatomic ion. There are a few others, but that's probably the most common positive one that you come across a lot. So what does that mean? It means that the vast majority of polyatomic ions are actually negatively charged. So in most cases, what ends up happening is you will end up with a polyatomic ion that's negative, and it will hook up with a metal that is positive. So more often than not, when you're dealing with polyatomic ions, you will have this combination of a metal and a polyatomic ion, which means, as we talked about earlier, if I had to decide between the metal and the polyatomic ion, which one is most important in terms of naming? What was most important in the first two? Metal. So the metal here is, again, what is most important. The polyatomic ion, it's all about, you're just going to use the name. So you don't have to really worry too much about it. It's just going to be whatever the name of the ion is. So what usually will happen in this situation is you will have to decide, is that metal a type 1 or a type 2? And ultimately what you're deciding is, do you need a Roman numeral or not, right? So that is essentially what you're going to try to determine here. So for example, let's say I didn't have the ammonium with it, but I had this, NaNO3. That is a metal, right? And that is our polyatomic ion. We could split it right there. We would have our NO3 minus, and we know that sodium is group 1, which has an Na plus, right? So ultimately, we're putting together +1 and -1, which is why we have one of each, right? So here we have a metal and a polyatomic ion. My metal there, sodium, do I need a Roman numeral for? Sodium is what type of metal? It's a type 1, which means no Roman numeral. So to name this, I'm ready to name this. This would be sodium nitrate, right? Just like we did with type 1, basically same rule. I don't need a Roman numeral, just use the whole name of the metal and the whole name here of the polyatomic ion. Now, let's say I had this. Now, when I look at this, right, iron, which is Fe, is a metal. We still have the polyatomic ion there. That metal, iron is a type 1 or type 2? It is a type 2, which means I do need a Roman numeral. So you still have to do what we did with type 2, which is I'm not sure what the charge is, but when you look at your polyatomic ions, you will know what the charge of NO3 is, which is NO3 minus, right? By the way, I have how many of those NO3 minuses? Yeah, that's what we got going on here, right? So I don't just have one, but I have two. And that, by the way, gives me a grand total for the negative part of this, a minus. So we were doing this guy, I think, right? FeNO3 right? So once again, we had this, and we did have our two of these. And again, that's going to give us -2 is +2, which means just like we did with type 2, we would have to go iron Roman numeral 2, right? And again, doesn't matter how many of those polyatomic ions you have, you're just going to use the whole name. Once again, no prefix here, right? So no prefix like before. This would be iron Roman numeral 2 nitrate. By the way, we do need to put parentheses, as you see in this example here. Whenever you have more than one polyatomic ion, you usually have to put parentheses around it and the number on the bottom to indicate how many you have. That basically means you have two of these polyatomic ion units. The reason we have to do that is if I did not put the parentheses and just wrote it like this, what does that mean? I have 32 oxygens, which I don't think is what I mean in this situation, right? Because I can clearly see here I only have 3, and 3 is 6, right? And I have a couple of these. So we definitely should always put the parentheses around it, any polyatomic ion. And by the way, it does get multiplied in, yeah? So 2 nitrogens and 6 oxygens. And again, there's the 3 and 3, which is the 6 oxygens, 1 nitrogen, 2 nitrogens, again, is what that means, yeah. Any questions on that there? All right. So here's a table from your book of some polyatomic ions. And like I said before, most of them on here are going to be negatively charged or a few positively charged ones. There are patterns of ways to sort of remember these and sort of help yourself, get a better understanding and handle on these is by grouping them sort of together. And there are ones that are related to each other. And there's kind of two ways that they're related to each other, or two sort of patterns a lot of times. There are ones that sometimes are just like two of them that are related to each other. And there are ones that are like four of them that are related to each other. So for example, if we took NO3 minus that we just saw, which once again has a -1 charge, that is nitrate. There's also one that's related to it that is NO2 minus, and that has nitrite. For example, if we have SO4 2 minus, once again, all those guys are going to stay together. The whole thing has a -2 charge. That is known as sulfate. SO3 2 minus. That is known as sulfite. First off, what is the difference between these two guys? The only difference is the number of oxygens. Yeah, they both have a -1 charge, right? They both have a nitrogen. The only difference is the top one has 3 oxygens, right? And the bottom one has 2. How about these two? What is the only difference between these two? The number of oxygens. They both have a -2 charge. They both have sulfur, and one has 4 oxygens and one has 2 oxygens, or 3 oxygens in this case. So in a grouping of things that are related to each other by, say, 2 of them, the one that has the most oxygen in that grouping will always end in 8. Like you ate too much, yeah? So it's the one with the most oxygen. The one in that grouping that has the least number of oxygens will end in ite, like we see here and we see here. So 8 is the one in a grouping that has the most oxygens, and ite ending is the one that has the least. So if it ends in 8, most oxygens. If It ends in ite, least oxygens. Yeah. Now, there's also some groups here that are related to each other by 4 things together. And for example, we'll take this 4-pack right here is probably the most common one. Maybe I'll go back this page and show you. This is ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. Again, every single one of these have a -1 charge. All these guys stay together. The only difference here is the oxygen. So in this case, we don't have 2 of them that are related to each other. We have 4. So you can kind of split it in half. Everybody to the right here has the least number of oxygens, which means should it end in ate or ite? Ite. So this would be like chlorite, because there's chlorine involved, right? This would also be chlorite. But clearly you cannot have the same name for 2 different formulas. So when you have 4 things that are related to each other, the one with the least number of oxygens will end in ITE, but it will also start with hypo. We have hypo and ite. Going the other way with our ClO4 minus and our ClO3 minus, those are the ones with the most oxygen, which means they should end in ate, right? So this would be chlorate because it's chlorine, right? This would also be chlorate. But once again, we cannot have the same name for 2 different things. So in a grouping of 4, the one with the most oxygens will also start with something different. It will start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. By the way, that Cl is what type of element? That is a halogen, right off the periodic table, which means if you had to take a guess and I swap out the chlorine for a bromine, what would that be called? Yeah, instead of chlorate, that it would be bromate. Yeah. By the way, if you swap it out for an I, it becomes iodate. So you could actually swap it out for any of those guys in the halogens. They're all named kind of the same way. So other things that you will sometimes commonly see is, for example, if you look on that list, you will see something that is CO3 2 minus. That is carbonate. And if you put an H plus kind of on top of carbonate or in front of carbonate, you will get HCO3 plus 1 and -2 leaves you a -1 left over. I basically just put what element in front of carbonate? I just put hydrogen. So this is hydrogen. Hydrogen, spelled right there. Hydrogen carbonate. Because I put a hydrogen basically in front of it. Hydrogen carbonate, by the way, is old school name, some bicarbonate for all that heartburn you're having right about now. Yeah. So the bicarbonate is sometimes used. So sometimes people will use bi instead of the hydrogen. They also will do that on sulfate. So you could have something like sulfate here. And you also could put a hydrogen in front of it, HSO4 minus. Remember the sign changes here. And that would be known as hydrogen sulfate or bisulfate. It is sometimes referred to still today. So sometimes you'll see that bi kind of used instead of hydrogen. And again, it basically just means you have a hydrogen in front of it. So these are some things that you sometimes will see. Other things, there are some on that table that actually do end in IDE, like OH minus is hydroxide. So there are some polyatomic ions that end in IDE, CN minus, a little cyanide right here. So there are a few of those that do end in that, but a vast majority of these will end in ATE along the way. So how can you kind of help yourself? You know, if you remember, for example, let's just say he decided like, I'm going to remember like all the 8s, right? So I remember sulfate, right? And that is sulfate. What I know is 8 is the most oxygens, which means if I need sulfite, the only thing that should change is I should take off 1 oxygen. Everything else will remain the same. And now you could get yourself to sulfite pretty easily, right? Or if you want to remember sulfite, you know, if I want sulfate, I just add an oxygen, right? So sometimes it's good to remember maybe one of them, the 8s or the ites, and know how to adjust it. For example, we did our sulfate, our sulfite, right? We could have this, which is, by the way, phosphate. What would phosphite be, by the way? PO3, 3 minus. Remember, nothing changes other than the oxygen, right? What would perphosphate be? One more up, right? So that's actually one more up, right? That's kind of like our group of 4 that we had. You would actually be PO5, 3 minus, right? So sometimes, you know, when you're dealing with these, if you want to remember like one of them and know how to adjust them is sometimes, you know, just add an oxygen, take an oxygen off, depending on which way you want, is sometimes quite helpful. So if we have some here, well, here's some more tables. So here's another table here as well. So I didn't write on this one, so maybe we'll go on this one. Yeah, we'll do this one. So why don't you try some here? So let's say we had, let's say we did have CuOH2. Why don't you give the name of that? Why don't you give the name of Na2SO4? Why don't you give the name of Fe3PO42? And why don't you write the formula for potassium chlorate? And why don't you do calcium hydrogen carbonate? All right. So come up with some names. Most of those. So since we're getting down, let's take a look at it here just to see and kind of finish this up here. Again, we want to take the same approach. So I got copper, which is a metal. I see a polyatomic ion. So again, whenever a metal's involved, we want to look towards that. So copper, we need to decide, do I need a Roman numeral or not? What do you think? I do need it. It's a type 2 metal. So we want to kind of do the same approach. I'm not really sure what it is, but I come over here, hydroxide, OH minus. That means I have an OH minus and not one, but 2 of them, right? That's going to give me a -2, which means my copper here is going to be +2. And again, that is all I need to name this. We're going to go somewhere. I don't know where we're going to go. Maybe over here. Copper, Roman numeral 2 for the charge on the copper. And once again, it doesn't matter how many polyatomic ions you have, you're just going to use the name of it, which as we can see here is hydroxide. So this would be copper, Roman numeral 2, hydroxide. Any questions on that one there? Coming to the one over here, that is Na, which is sodium, which is a metal. SO4 is sulfate, which is a polyatomic ion right about there, right? And that is the metal we want to look at. So sodium is group 1, which means it's a fixed positive charge. It's a type 1, which means I don't really have to figure out anything on this one. I could just use the whole name of the metal, which is sodium. And once again, we're going to go whole name of our polyatomic ion. So this would be sodium sulfate. The reason we have 2 sodiums in this case is because the sulfate has a -2 charge, right? And the sodium has a +1 charge. So we need 2 of those sodiums to balance out the charge, just like any ionic compound. We again do not use prefixes with this. The only time you would have a prefix and maybe a metal is if the polyatomic ion, like this guy, has an actual prefix in its name. Other than that, you'll never have a prefix with it. Here, this is iron, which is a metal, and phosphate, which is a polyatomic ion. Iron is a transition metal, which means it's type 2. That means that we need to go with that. We have phosphate here, which is PO4 minus, and we can find that right there. And we don't have just one of them, but we do have two of them there, and that's going to give us PO4 minus. So ultimately for our negative, -3 -3 is -6. We don't just have one iron in this case, but we actually have 3 of them. That means each of them is how much? Yeah, each one is +2, right? +2, +2, +2, +6. The name of this is iron Roman numeral 2, not 6, yeah? The one each individual charge on the metal +2. And again, phosphate, right? Any questions on those names there? Now that we have the name, we're just going to kind of put it together properly. So copper Roman numeral 2 means we have a copper with a +2 charge. That is what the Roman numeral means. Hydroxide is OH minus. So once again, we need to put it together to get to 0. This is -1, which means we need not one of them, but we need 2 of them to balance out that +2 charge of the copper. And that will give us, I'll come below, Cu. We will need parentheses because we have more than one of the polyatomic ion, right? So we got to put those parentheses around it. If you just have one, you do not need the parentheses. Any questions on that one there? We have potassium chlorate. Potassium is group 1, which means it has a +1 charge. It's a metal. Chlorate's one of those 4 that we talked about. ATE means it has one of the most oxygens, but not the almost. So it's ClO3 minus. That is a -1 and a +1, basically. We're good to go by just slapping those guys together, yeah. And we just need one of each. Again, we do not need parentheses here because we have one of each of them. +1 and -1, right, gets us to 0 in this case, yeah. Lastly, here we have calcium, which is +2. And hydrogen carbonate is somewhere up here, I think. Right there, hydrogen carbonate. And that is HCO3 minus. So in this particular case, we have -1 and +2. That means we actually need one more of the bicarbonate. And we would need a total of 2 of those, right? 1 and 1 is -2 and the +2. So we'll put it together here. Ca, we will need parentheses, HCO3, and the 2 on the bottom there. Again, telling us we have 2 of the hydrogen carbonates and 1 of the calcium at +2. And again, the goal here is they're all still ions, so we got to get it to 0.